Number one, look at the graph and see which of the following functions could describe it. So each A, B, C, D are all given to you in standard form. Standard form, the general model for a function in standard form that's quadratic is y equals ax squared plus bx plus c. And probably the first place to start is the c, which is your y-intercept. So let's look at all these c's. And a, b, and d, the c's are all negative, so that means the y-intercepts are negative. C is your y-intercept, so C is where this parabola is eventually going to cross the y-axis. So C is going to happen somewhere clear up here. So I'm going to go with 11. 11 makes sense. None of these are reasonable because these would all mean your parabola is going to cross the y-axis at -5, -2, -1. And that does not describe the picture. Okay, write the functions. So let's kind of review from chapter 1. Let's examine and see how fast they're changing. 2 to 0. That's going down to 0 to -2 down to. Okay, so this function, each time the x changes once, the y's are changing twice and they're going down. So this is a linear function. The model for all linears, y equals mx plus b. I notice linear is changing at a constant rate. All I've got to do is find m, which is the rate of change, how fast it's changing, and b, which is your y-intercept. Okay, the rate of change is simply the change in y's. So y sub 2 minus y sub 1 divided by your change in x's, x sub 2 minus x sub 1. And my y's are changing -2, my x's are changing 1. So my rate of change is -2. My b is the y-intercept, and that, where's my y-intercept? My y-intercept is the mate of 0. So my rule is going to be y equals a -2 times x plus a -4. And I can test it. If I punch in a 3 and I multiply it by a -2, that gives me a -6. If I do -6 minus 4, it should give me a -10. And it does. Okay, now this next pattern is probably going to be quadratic. How do I erase? Okay. I'm going to have to get a calculator. So my x's, they are not a trick question. So they're just changing once every time. Up 1, up 1, up 1, up 1. So let's look at the y's. -27 to 9. How much is that? That is going up, right? So I'm going up 18. -9 to 1. That's up 9. 1 to 3. That's up 2. 3 to a -3. Now we're going to turn around and start to go down 6. -3 to -17, is that -14? And 17 to 39, how much is that? That's down 22. Okay, so now I'm going to examine those again. 18 to 9. That's going down 9. I wonder if I messed up. 9 to 2. Is that going down 7? But if it's quadratic, I want this all to be -9, -9, -9, -9. So I think I messed up. Okay, and I think where I messed up is right here. From a -9 to a +1, that didn't change 9. That went up 10 times. So, and hopefully that's the only spot I messed up, but who knows. But the big hint is, because it's quadratic, the second change needs to all be the same. So you gotta be precise with your calculations. Sometimes that's hard to do. Okay, 18 to a 10. That went down 8. 10 to a 2. That went down 8. Okay, that's looking better. 2 to a negative 6, that went down 8. A negative 6 to negative 14, that went down 8. And a negative 14 to a negative 22, that went down 8. Okay, so now I feel pretty good about it. Now I know it's a quadratic, and if it's a quadratic, the standard model, the standard form is y equals ax squared plus bx plus c. And kind of like your linear model, y equals mx plus b. These two guys are your constants, your numbers with no letters attached, and they are the same thing. They're both y-intercepts. So c, I'm going to find c first. So I need to find the value of a, the value of b, the value of c. C is my mate of 0, just like b is the mate of 0 on a linear pattern. So my c in this case is 3. And the next one that's not too hard is a. I'm going to find a. A is half of your second change. So a is going to be my negative 8. That's my second change. It's constant. I divide that by 2. It's going to be a negative 4. So here we go. I got y equals a negative 4x squared plus bx plus 3. And now my next move, I've just got to figure out the value of b. And to find b, you just choose a point from your, we do this all chapter long, choose a point and plug it in. I'm going to take this 1 and replace it for x. And I'm going to take this negative 3 and replace it for y. And I'm going to get this, a negative 3 equals a negative 4 times 1 squared plus b times 1 plus 3. And then do the arithmetic, and you should have negative 3 equals a negative 4 plus b plus 3. And now I'm going to scoot over here. A negative 3 equals a negative 1 plus b. So minus 1 plus 1 plus 1. So b equals a negative 2. And if you know the value of a, the value of b, the value of c, you are done. Your model, your function is going to be y equals a negative 4x squared minus 2x plus 3. Okay, now, this is what's new to this chapter. Looking at a graph, we talked all about how quadratic patterns look when they're graphed. So, given a graph, can you write the function? And then why are linear straight and quadratics curved? So let's look at, let's do the linear first. Okay, the linear, if you look at a couple points, and your points have got to happen right on intersections. So I think on that line there's 3. And now I'm going to connect from dot to dot. How much am I changing? How fast is it changing? And am I going over 1, 2, 3, 4, 5? I'm going over 5 and I'm going down or up 3. 2, 3, 4, 5, and 3. Okay, the slope on a linear is the model y equals mx plus b. The slope is the exact same thing as rise over run, the change. And so my fraction is going to be 3 over 5. 3 is my rise, 5 is my run. And is it increasing or decreasing? Is it growing or is it shrinking? And I know that it's shrinking because it is falling. As I go from left to right, it's going down. So it's going to be a negative growth. So my m is negative 3/5, and my b is your y-intercept. So your b happens at 3. So the model is going to be y equals a negative 3/5 x plus 3. That model describes that linear pattern. Why is a linear represented with a straight line? Because your change is constant. Each time you go over 5, you're going to go down 3. Over 5, down 3. Over 5, down 3. Your change never changes. It's going to be constant. Okay, let's look at the quadratic. The quadratic, this quadratic, if you find some points, you got a point right there. Looks like you got a point there, and then not again until clear down here. So, if you try to do your rise and run, I'm going over 1, but I'm going down 3, and then I'm going to go over 1. And this time it's not down 3, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So every time you go over 1, it looks like you're going down 3, then over 1, down 9, then over 1, down 15 or something. Who knows? Every time you go over, you're going to go further and further down. So your change is changing from point to point. Okay, now I've got the vertex. I've got this most important point. So I'm going to use vertex model. The model for vertex is y equals a x minus h squared plus k. So I'm going to plug in my vertex. My vertex is right here. It is over 4 down 1. I'm going to plug it into my model, and it's going to now look like y equals a x minus 4 squared minus 1. Okay, now when you're using vertex form, you got to be tricky about the sign of my 4. Is the sign positive or is the sign negative? And because I went right 4, my sign has to be negative. That one's kind of backwards from your intuition. So that's something definitely to remember. Okay, now the only thing you got to do is find the value of a. Are you speeding up this growth? Are you timesing it by something? So if you want to find a, I'm going to take this point, for instance. This point, if I'm looking at a table, this point is over 3 down 4. So I'm going to take that point and plug it in, just like we did in chapter 1. We took a point and we plug it in. Plug that in for x, plug this in for y. That's kind of a common theme. If you know a point, you can always plug it in to get more data. So I'm going to take this x as 3, and I'm going to plug it into my model right there. I'm going to take this y as negative 4, plug it into my model right there. So I'm going to have this, a negative 4 equals a times 3 minus 4 squared minus 1. Okay, 3 take parentheses first, 3 take away 4 is negative 1. Then you got to square it. Negative 1 times itself is a positive 1. So I got negative 4 equals a times a positive 1 minus 1. Okay, now you got to solve for a. So I got to get rid of this minus 1 times 1. Get rid of the minus 1 first. Plus 1, plus 1. And 1a, or just a, you don't even need to write the 1. 1a is equal to a negative 3, which makes total sense. Y equals a negative 3, x minus 4 squared minus 1. Makes sense because I know a has to be negative because it's concave down, it's opening down, and you're speeding it up by 3, you're timesing everything by 3, so it's going to be kind of skinny. And if you want, you could do the arithmetic and change that to standard form, but that's not necessary. We'll just leave it in vertex form. Okay, what about this question? Why is it a linear line is straight, but a quadratic is curvy? Okay, it's curvy because we talked about first, you're going over 1 down 3. Then the next time is over 1 down 9. So each time you go over, it's going to get steeper and steeper. But why is it reflexive? Why does it hit some maximum or minimum and then turn around and repeat itself? So this happens to be a maximum. Your vertex is a maximum because that's the highest it is ever going to get. And it is reflexive, or it is symmetric, because of the square, which is by definition quadratic. So anytime you square something, if you start off with the basic, just x squared, if you do 2 squared, that's going to give you 4. But there is another number that will give you the same answer, and that is a negative 2 squared. If you do a negative 2 squared, that will also give you 4. So you're getting the same answer by plugging in totally different numbers. In this case, if you look at this table, into this quadratic, which was dilated and shifted horizontally and vertically, so it's kind of a mess, but I plugged in a 3 and I got out a negative 4. But I also plugged in a 5 and I got out a -4. So you're plugging in two totally different numbers, but they're giving you the same answer. Okay, can you stare at the table and find the vertex knowing that this is a quadratic? So I guess you assume it's quadratic, and the vertex should be right here. So it looks like it's, what are we doing? Growing? And it turns around right here and starts to shrink. So if you looked at an image real quick, if -1 up 4, and then -2, 3, and hold on, 0, 3, -1, this is messing me up. -1 up 4, that's this dot. Oh, -1 up 4, that's not that dot. Let me start over. Okay, -1, I think that's my vertex, but I'm just double checking. -1 up 4, there's my vertex. Okay, now -2 and 3, so -2 right there and 3, and that's this dot I just did. Now I'm going to do this dot, 0 and 3. Okay, that looks better. So my vertex, and then it's going to look something like that. So my axis of symmetry, the equation for my axis of symmetry. My axis of symmetry goes right through the vertex. It is a vertical line that intersects the x-axis. So my equation for the axis of symmetry is x equals, wherever it goes through, it's x equals -1. The number of x-intercepts, this parabola will cross the x-axis 2 times. The vertex is going to be a minimum or maximum. This one is a maximum because that is the highest point of my parabola. Okay, now let's look at this one. See if you can find that middle point where it turns around, and I think it is right here. So just to kind of check, I'm going to sketch real quick. Over 4 down 2, 1, 2, 3, 4. Over 4 down 2, there's my vertex, and I'm going to go 1 above it, 1 below it. So over 3, 1, 2, down 3, and over 5 down 3. So there we go. Your parabola looks something like that. Your axis of symmetry goes right through the vertex. It is x equals 4. The number of x-intercepts, this parabola never crosses the x-axis, so it has 0 x-intercepts. And is it a maximum or minimum? It is also a max. A minimum would look like this. That would be the lowest point of your parabola. Okay, now let's figure out your shifts. Let's look at a parent function x squared. So if I plug in a -2 to the model, -2, and then square it, -2 times -2, that's 4. -1 times -1 is 1. 0, 1, and 4. And if I plug, let me plot those. -2 up 4, over 1 up 1, 0, 0, over 1 up 1, over 2 up 4. Okay, that is my parent function without doing any funky things to it, just x squared. Now, if I subtract before I square it, that effect has a horizontal shift. And the question is, why is it when it's -2, does it actually shift everything to the right? How come it does not shift everything to the negative, to the left too? And that's kind of a tricky question. So, if I -2 before I square it, so I'm going to start up here with the 2. If I plug 2 in and take away 2, I'm really asking you to do, what? I'm really asking you to do 0 squared, which is 0. I'm really asking you to look at this one, which happens to be 2 before in the table. So if I want you to plug 1 in, so the first thing is you do is 1, you take away the 2. That is a negative 1. So I really want you to look at the negative 1. So we're at 1 right here. It's going to have the same answer as negative 1 did, which was 2 earlier in the table. So when I plug in a 1, it's going to give me a 1. So now look at this, 0. So when I plug in 2, first move is I got to take away 2, which is you look 2 earlier on the table. So 2 take away 2 is 0. I really want you to square 0. So when I squared 0, when I plugged in 0 to the original, it gave me a 0. This dot right here, 0, 0. But when I plug in 2, so now I'm sliding 2 times, I'm plugging in a 2, and it is giving me a 0. And when I plug in a 1, it is giving me a 1. When I plug in 0, what's going to happen? So 0 plugged in, first thing is 0 take away 2, that's a negative 2. So what you're looking at is a negative 2 squared, which is 4. A negative 2 squared is 4. So 0 is giving me the exact same answer that negative 2 did. Okay, negative 2 gave me this answer. Negative 2 gave me an answer of 4. But now 0 is giving me an answer of 4. So it is taking each point and it's shifting it right 2 units. So why in the world do you subtract before you square it? It shifts it to the right. And the reason is because when you subtract before you square it, you're actually looking at what was squared 2 times earlier on the original parent function. So if I'm wanting you to look at 2 on this adapted model, I want you to plug in 2, but then I want you to take away 2. I want you to look at what happened when 0 was plugged in. Okay, what if you add or subtract after you square it? So vertical shift, so same thing. Your parent function, x squared, it's going to be 4, 1, 0, 1, 4. So 0, 0, over 1, up 1, left 1, up 1, over 2, up 4, left 2, up 4, over 3, up 9. So there's my parent quadratic. But now, what if I take the same number and I square it, so that gives me a 4, but then I take away 2. I take the same number, I square it just like I did here, so I square it. Negative 1 squared is 1, but then after you do that, it says you want to take away 2. 0, plug it in and square it, but then take away 2. So 4 take away 2 is 2. 1 take away 2 is negative 1. 0 take away 2 is negative 2. 1, plug it in, square it, just like we did here. 1, we plugged in, we squared it. But then take away 2. That's going to be 1, take away 2. So now look at these dots. It is taking each dot. So left 2 up 4, left 2 up 4 is taking that dot, but then it's minusing 2 from it. So it's going down 2. Taking this dot, minusing 2 from it, down 2. Taking this dot, minusing 2 from it, down 2. This dot, minus 2 from it. So it's taking each answer, because your answers are going to be the exact same, but after you get the answer, then it's taking that answer and it's moving it down 2. It's taking 2 away from it. So if you square first and then take away or add, it is just going to take all your dots and move them down or move them up, depending on if you add or subtract. Okay, what about a dilation? What if you take all these answers, so 4, 1, 0, 1, 4, 0, 0, 1, 1, left 1 up 1, over 2 up 4, left 2 up 4, over 3 up 9, left 3 up 9. Now, what if we take your answers? So the first thing you do is square it. You don't times until after you square. So I'm going to still get my same answers, 4, 1, 0, 1, 4. But then after you get your answer, double it. Times it by 2, times it by 2, times it by 2, times it by 2. So now if you double each answer, That's going to be 8, 2, still a 0, 2 and 8. So it's speeding up the rate at which it grows. So 0, 0 is still the same, but now instead of going over 1 up 1, I'm going to go over 1 up 2, and left 1 up 2, over 2 up 8, left 2 up 8. So your parabola is going to get skinnier. It is going to grow faster than your parent function, because your parent function, you just square it. Your adapted model, you square it and then you double it. So it's going to be skinnier. It's going to grow faster. Alright, number 8. Give me the function that represents this graph. So stare at it and ask yourself, you got 3 models: standard, vertex, and factored. The vertex is not on an intersection, so the vertex is going to be some kind of a decimal. So you are not going to use vertex form, because the only way to get the vertex is to guess. It's between what 2 decimals. You do have zeros or roots or x-intercepts, so you're going to use the factored model. The factored model is y equals a x plus or minus a root times x plus or minus a root. Okay, my roots are over 2, 0, and left 1, 0. There are my roots. Now when I plug them in, this is the trick. Y equals a x and a 2, x and a 1. The $1 million question is, what are these going to be? Are these going to be pluses? Are they going to be minuses? The sign. What is the sign going to be? So the 2 is actually going to be negative, and the 1 is going to be positive. Okay, I know that because when I make y equal 0, 0 equals a times, if I plug 2 into this, and 0, so I'm plugging 0 there, and I'm plugging 2 here, 2 minus 2, and 2 plus 1. Man, this board is going to drive me nuts. Ooh, I'm not sure what I did. Okay, when I plug 2 in for x, and 0 in for y, 0 equals a times 2, what did I have here? Minus 2 and plus 1. 2 minus 2 and 2 plus 1, I will get a times 0 times 2, which is equal to 0. And when I plug a negative 1 in there, I'm going to get 0 plug into there. Holy cow, this board sucks. 0 into there, so I'm going to get 0 equals a times negative 1 minus 2 and a negative 1 plus 1. There is my 0. 0 times a negative 3 times whatever a is going to be 0. So your roots and your function are always going to be opposite signs. Okay, now you got to find a. The only way you can find a is if you can figure out one more point. And there is a dot there and there's a dot there. So there is a dot on 0, negative 2, and there's a dot on over 1, down 2. So pick one and substitute it in. I'm going to pick this right here. So I'm going to plug negative 2 in for y. So negative 2 equals whatever a is times, and in place of x I'm going to put a 0. And I'm going to get this. Negative 2 equals a multiplied by negative 2 multiplied by 1, which is negative 2 equals negative 2a divided by negative 2 divided by negative 2. A is equal to 1. So my function is going to be y equals 1 times x minus 2 times x plus 1. And that is good enough. 9. Okay, they give you a function in factored form, and let's analyze it. Is it concave up or concave down? I'm going to go with concave up because a equals 3 And when A is positive, it looks like concave up. What are the x-intercepts? This is just barely what we talked about. Here are your roots, x minus 5 and x plus 2. So the question is, I know my roots happen right here somewhere on your x-axis, and I know my y's are 0. So if I take and plug 0 into this model, I want my answer to be 0. So what can I plug in place of x that will give me a 0? And I'm going to look at this one first, and I know if I plug in 5, that'll work, because 3 times 5 minus 5 times 5 plus 2 is going to be 3 times 0 times 7, which is 0. So that's one of my roots, over 5, 0. So see, it's kind of always opposite what it is in the function. My other root is going to be a negative 2. If I plug a negative 2 in for those x's, I'll get a 0 times negative 7 times 3, which is 0. So my x-intercepts are going to be negative 2, 0, 5, and 0. Okay, your line of symmetry. Your line of symmetry. So I'm going to sketch a quick graph. If my roots are at 5, 0, 1, 2, 3, 4, 5, and negative 2, 0, there are my roots. My line of symmetry is the midpoint of those 2 points. To find the midpoint is just the average. So I'm going to take the average of 5 and a negative 2. I'm going to add those together. 3, divide that by 2, and 1.5. So 1.5 is halfway between a 5 and a negative 2. My line of symmetry is x equals 1.5.